In 2023, British ice hockey player Adam Johnson tragically died after his carotid artery was severed by an opponent's blade during a match. The blade, less than 3 millimeters wide, claimed his life. Yet, on the ice rink, the same narrow blades can hold figure skaters weighing over 100 pounds, allowing them to glide gracefully on the ice and land steadily after a triple spin. How could such a thin, almost translucent blade become the sole point of support for a jump and landing? The answer lies sealed 4,000 years ago. In the frozen lakes of northern Europe during winter, to move faster while hunting or relocating, locals would grind down the ribs of deer and cattle, tie leather straps to their feet, and glide across the ice. Fast forward to the late Middle Ages. In the canals-lined Netherlands, craftsmen were the first to fix iron blades onto the wooden soles, ushering in the era of metal ice skates. Meanwhile, in far-off China, ice skating vividly records court ice ceremonies, showing the wisdom and achievements of different civilizations on ice. Modern ice skating is divided into 3 categories: figure skating, speed skating, and hockey. Figure skating takes the magic of the blade to its extreme. When we watch figure skating star Yuzuru Hanyu spin, he doesn't stay rooted to one spot on his foot, completely still. Instead, he moves slightly around the small arc of the front of his blade to find the most stable balance position. But the magic of the blades goes far beyond spin. During a toe jump, what appears light and graceful is actually the most ferocious part. The tiny serrations at the tip of the skates plunged into the ice, concentrating all his weight on a point the size of a fingernail, creating a stable foothold on the ice. He then pushed off, propelling himself into the air. It is these tiny toe picks that help figure skaters grip the ice firmly. If it were speed skating, which have no toe picks, and tried the same takeoff, the skater would just glide smoothly across the ice, making it difficult to launch themselves. Speed skating aims for long distance, stable, and high-speed gliding, while figure skating needs to bite the ice firmly in an instant to complete delicate and agile jumps. What are the laws governing the motion of the body after taking off from the ice? The answer to this question was revealed by Galileo in the 17th century. He discovered that all projectiles move along a beautiful parabola. This ancient law is perfectly demonstrated in every figure skating jump. From the moment the skater pushes off, their trajectory is dominated by gravity. No matter how they swing arms or pull legs in the air, they cannot change this predetermined parabola. This is precisely why coaches are so demanding of the takeoff technique. That decisive moment directly relates to the precious time available in the air, determining whether the athlete can complete the planned triple or quadruple rotation. When the parabola ends, the skater faces the challenge of landing. Television, slow motion often makes this moment appear as gentle as a feather landing. However, according to kinematic measurements, the ankles and knees bear several times, even up to 10 times, the impact of the skater's own body weight. If this hit had landed directly on a hard floor, the joints and bones would suffer. Therefore, the ice and blades together break down the energy into several parts, absorbing it gradually. The instant the skate makes contact with the ice, the tiny point of contact generates immense pressure, temporarily softening the ice. Then, the skate slides forward, spreading the contact from a point into a line. The friction and pressure between skate and ice dissipate this massive impact energy bit by bit, rather than slamming it all onto the knee in a single millisecond. That's why skaters bend their knees on landing, sinking down like a spring, allowing their muscles and joints to work with the blades to break down the impact into a longer, softer landing. This raises a deeper question. Why is ice so understanding? This question ultimately fell to 19th century physicists. A group of people, led by Faraday, became interested in what ice actually was. They conducted a now classic experiment. Take a large block of ice and place a thin metal wire in the middle. Attach weights to both ends. After some time, the wire slowly cuts into the ice, eventually passing right through the middle. But when you pick up the ice, you'll find that it hasn't been cut in half. Instead, it's rejoined as if the knife mark had been stitched back together. Faraday thus realized that ice is not a completely hard block of brick, but a substance that can be softened locally under pressure and then returned to a solid state. This phenomenon of water turning into ice under high pressure and then freezing again once the pressure is released was later called as regulation. If you look back at the blade marks on the ice rink, you'll understand better. The grooves cut by the skates are only temporarily etched and will slowly close and heal in the cold. In the mid-19th century, the Thomson brothers delved deeper and discovered that the greater the pressure, the slightly lower the melting point of ice. Back to the ice rink, you'll find that the blades are very thin. A person's weight is concentrated on a narrow metal blade. This edge doesn't leave a solid mark on the ice, but rather a temporary track that can be slightly rearranged and softened. As the skaters move on, these disturbed ice molecules would gradually return to more stable positions. The groove becomes shallower, and the surface becomes firm again. Once the ice repair truck arrives at halftime, it scrapes away the stirred-up ice chips and polishes the surface again. The ice surface, previously etched with grooves and crevices, quickly becomes like a blank sheet of paper, waiting for the next skater to write a new arc on it. From Galileo's description of parabolic motion to Faraday's discovery of the miracle of re-icing, to the Thomson brothers' revelation of the pressure melting principle, and finally to the silent self-healing of the ice surface, all of these together constitute the invisible wings that allow ice dancers to fly. On the ice, we jumped, spun, and landed, again and again, the blades carving delicate lines into the ice, which were quickly smoothed over as if they had never existed. Isn't life just like that? The choices we've made, the risks we've taken, the people we've loved, the detours we've taken, most of them leave no trace. They're just a stroke on the ice of time, then silently erased. This is a physical law that no one can defy. But the moment you step onto the ice again, knowing that these marks will eventually disappear, will you still choose to leap?